Today's Krishna Bharadwaj Memorial Lecture, the 28th in the series, will be delivered by Professor Somak Raychaudhury, the Vice-Chancellor of Ashoka University and one of India's foremost astrophysicists. The title of the lecture, you would have noticed, is The Future of the Universe. We are greatly honored to have Professor Raychaudhury with us today. Professor Raychaudhury has undergraduate degrees in physics from Presidency College, University of Calcutta, and Trinity College, University of Oxford. He holds a PhD in astrophysics from Churchill College, University of Cambridge. After completing his doctoral work, Professor Raychaudhury moved to the Harvard-Smithsonian Center for Astrophysics located in Cambridge, USA. There he was part of the team that built the Chandra X-Ray Observatory, which is, as NASA's website says, and I quote, part of NASA's fleet of great observatories. Professor Raychaudhury's research spans a range of topics in cosmology and astrophysics. His pioneering work explores how stars form and evolve, as well as how galaxy clusters, each containing millions of galaxies, themselves composed of millions of stars, change over time and space to shape the universe we observe today. He has studied even larger structures such as superclusters made up of vast number of galaxy clusters and their crucial role in cosmic evolution. Further, his work examines supermassive black holes. These are objects 1 million times more massive than the Sun that reside at the centers of galaxies, including our own Milky Way. Professor Raychaudhury was also part of the team that discovered the Saraswati supercluster of galaxies in a few years back. Professor Raychaudhury has received numerous prizes and scholarships, indeed too numerous to list here. He has held several prestigious positions, to mention but a few: tutor in astrophysics at Lowell House, Harvard University, research fellow and later visiting fellow at the Institute of Astronomy, University of Cambridge, and postdoctoral research fellow and later visiting fellow at the Harvard-Smithsonian Center for Astrophysics. He is a fellow of several honorary societies, in particular the European Astronomical Society, the Royal Astronomical Society, and the National Academy of Sciences. Besides being a brilliant academic, Professor Raychaudhury is an institution builder par excellence. When Presidency College, Kolkata was upgraded to an independent university, he returned to India from the University of Birmingham, UK, to serve as Dean of Faculty of Natural and Mathematical Sciences at Presidency University. In 2015, Professor Raychaudhury became the 4th director of the Inter-University Center for Astronomy and Astrophysics, an institute that is globally recognized for its research in the field of astronomy and astrophysics. In 2022, Professor Raychaudhury was appointed the Vice-Chancellor of Ashoka University. Amazingly enough, in the midst of all of this, Professor Raychaudhury has made time to establish and develop the Indian Astronomy Olympiad program, thereby nurturing school-level talent in the field of astronomy. Engaged in extensive outreach activities, including writing regular columns for the Hindustan Times and other dailies, and has co-chaired the committee that prepared for the Government of India the Vision Document 2024 for Astronomy Research in India. Please welcome Professor Raychaudhury.
Okay, thank you very much, and thank you, good evening. Thank you very much to the organizers for such a resounding introduction. It can only go downhill after that. Wonderful to see everybody here. You could have done so many other things on a nice evening in Delhi, but I'm glad that you're here. I'm also very deeply honored to be giving this Krishna Bharadwaj Memorial Lecture, very august occasion. You heard that I was the director for a long time of the Inter-University Center, Astronomy Astrophysics in Pune. Actually, one of the earlier lecturers in this series was Professor Jayant, who was the founder of IUCA and the first director, and of course my first boss when I came back for the first time to work in India as a young lecturer at IUCA in the 90s. So I'm very happy to bring astronomy back to this series today. I said that I'm going to talk about the future of the universe. People get bogged down a lot thinking about what's going to happen in the next 10, 20, 50 years. And of course, very legitimately, we are worried about what's going to happen to humankind, with the environment, everything around us. The good thing about being an astronomer is that I deal with billions of years. I'm not that worried about what's going to happen, so I should, in the next few years. And so today I'm going to talk about the time scale of billions of years. And that brings me to the fact that if I want to talk about what's going to happen to the universe, and of course it will be based on what we know now, based on the kinds of science that we do. Of course, everything depends on the amount of physics that we can apply to the rest of the universe. It's rather arrogant for an earthbound scientist to say, look, I know that this law of physics works in my laboratory. I can actually apply that to the rest of the universe and try to understand the entire thing. But a lot of it works, as you can see. A lot of the physical principles that we use in our daily lives actually explain a lot of the universe. And as an astronomer, one of the problems I have comparing my work to other scientists, and there might be many people here who are biologists or chemists or physicists of other kinds, that who can work into the laboratory and actually handle their experiments. They can change their experiment. They can repeat their experiment. As an astronomer, I cannot. I cannot even go and touch anything that I work on. And I certainly cannot repeat the experiment. There's only one experiment, and that's the universe. We're stuck with it. And we have to understand the universe based on what the universe throws at us. I can't change that either. I can't turn up the volume, for example. And that is the kinds of radiation that comes to us, and we try to understand what's happening out there from them. And you'll see some examples today. But to begin with, when we talk about what's going to happen to the universe, we also have to know how far we've gotten in the history of the universe, and that is the past of the universe. So in the Judeo-Christian tradition, from which most of our science really comes, the Christian tradition people are very, very clear. They knew exactly when the universe started. If you see, Archbishop Usher actually gave the date 4004 BC, 26th of October, when the universe started. And this was not just common belief. I mean, this was almost everybody believed in this, in that tradition. Isaac Newton, who is one of our greatest icons, wrote a whole book on how the universe is only 5,000 years old. Right? So not everything Newton did is right, by the way. And one of them was this completely wrong book of hundreds of pages, where from biblical tradition, he tried to establish that the universe is 5,000 years old. Now that came to a real head at the middle of the 19th century, when Darwin, sorry, I'm getting wrapped up here. Okay, when Darwin was about to propose the theory of evolution, and even in his first version, which actually went through many, many changes, he actually required that the universe had to be at least 300 million years old, if not a billion, because of the slow nature of changes that happen in species. Right? At that time, there was quite a lot of debate as to what the age of the universe was. The best estimate was from the physicists, was from Lord Kelvin, who the best he could do was 20 million years old. And this he did by assuming that the Earth, rightly, was a part of the Sun. The Earth and the Sun were formed at the same time. Kelvin thought that the Earth was actually a fragment of the Sun, which it isn't. The Earth had cooled to where it is now after having broken off from the Sun. And so, knowing that the Sun's temperature is 6,000 degrees, he calculated how fast rocks cool, and made this calculation that to come to the current temperature of the Earth, it would take about 20-30 million years. So this, of course, was not enough for Darwin. And so one of the major oppositions to Darwin's theory was that, of course, the Earth is not old enough. And the people who came to Darwin's rescue were not the physicists, but the geologists. And they looked at the structure of the Earth to show how rock forms by sediments, and then showed that in order to form the complexity of the rocks that we have on the Earth, one needed billions of years of time. And slowly that established that the Earth is about 4.5 billion years old. And so the universe has to be older than that. But on Earth, Darwin could establish the theory of evolution. Remember, this is the late 19th century. Radioactivity was not detected till the early 20th century, so radiocarbon dating and all that kind of stuff hasn't come yet. This is long before that. Yeah? And astronomers would then establish the age of the universe much, much later. That would be in the 1930s. So it's actually the geologists who told us about how the Earth's various phases would actually lead up to a few billion years old, and you can see this whole timeline that was established later. And astronomers, as I said, we try to understand the universe through looking at the sky and to understand what we see in the sky. And so this is a typical view of astronomy, right? This is all we have. We can't go and touch those stars. We can build telescopes and detectors and then study these specks which are stars. Now you also, to put things in perspective, to understand what a star is and what happens in the star that produces the light, had to wait till the 1950s. Because we had to understand nuclear fusion. We had to understand nuclear reactions. We had to go through Oppenheimer and the nuclear bomb. And then we understood how stars work. So this is a very, very new subject, astrophysics. If you look at the current deepest views of the universe, you will see that this is a normal naked eye view of the sky taken with a small camera, and you can see everything that you see in there is a star. This is the James Webb Space Telescope, the biggest instrument we have in space, the deepest view of the universe till date. This was taken last year. And you can already see there's a big difference between what you see here, which is all stars, and what you see here, which is all galaxies. There are only, I think, 2 stars. There's one star. That thing is a star. Everything here in this picture, that's another star. Everything here in this picture is a galaxy, and each galaxy has 100 billion stars. Right? And this was established slowly in the last 200 years by people who, with small telescopes, studied the sky. And I'll give you the story of how that came to being, how we understood that we live in a galaxy which actually is made up of lots of stars, something that we didn't know till the 1930s. But the story starts in the late 18th century, in the 1780s, 1790s, by these 2 people. William Herschel, very unusual people. William Herschel was a musician. He was an organist at a cathedral in Bath, in England, a German who was a musician. And his hobby was building telescopes in his backyard. Right? And I can't think of, and he built the largest telescopes in the world as a hobby in his backyard. I can't think of that happening now. Building the largest telescopes in the world are $1 billion, right? And so he was building these telescopes, and of course he became famous because he discovered Uranus. And once you discovered a planet, then you become very famous. He got some money from the government, and he started building larger and larger telescopes, and he started studying the sky, And he realized in the sky there were these stars that twinkle, and then there are these stars that are diffuse, which don't twinkle. And these he called nebulae, fuzzy things in the sky. At the same time, Charles Messier in Paris was trying to do a very different thing. He had been asked by the king to identify fuzzy things in the sky that looked like comets, because in those days discovering a comet was a big thing. And there were people discovering comets, claiming to discover comets, but most of them were not, because there were all these other fuzzy things in the sky. Comets come and go, but you see these fuzzy stars. And so Messier made a list of things which were not comets, but also not stars, right? So these two are still used by amateur astronomers. Anybody who's looked through a telescope, deep sky, etc., would use either the Herschel list or the Messier list to see your nice, objects in the sky that are not twinkling stars but actually have structure in them. Now, I've taken 4 of these objects which were in both people's lists, and you can see what the basic problem of astronomy is. All four of them were classified as the same thing by both of them 200 years ago. However, they are very, very different things. So for example, that's the Crab Nebula, which is actually a single star, but it has exploded, and that is why it's a fuzzy thing. At the end of its life, a star explodes and is turned into, we now know also that this explosion happened in 1054 AD on the 4th of July, but it now looks like a fuzzy object. The same size, and you have something called Messier 3, which has a million objects, million stars, and it's a cluster of stars. But to a small telescope, it looks like a fuzzy object in the sky. Here's a planetary nebula, which is a star at the end of its life, losing most of its matter, and it's floating around in space. That's something that's going to happen to our sun in about 5 billion years. Single star, million stars, and then that's what I call a galaxy, which we now know are the fundamental building blocks of the universe. These are the things which, like molecules, are the basic units, and they have a billion stars in them. Billion stars, million stars, one star. They look the same on the sky. So you have to know how far away they are. And that has been one of the major problems in astronomy, to find out how far away something is, and then you figure out how big it actually is. The sun and the moon are the same size on the sky, half a degree. However, they're two very, very different things, right? So that was one of the first steps that was not established till the 1920s and 30s, and people started. And one of the things that I'm going to tell you is this main problem of our finding out how to measure distances to things that led us to understand what these things are. So till about 100 years ago, even when Einstein is publishing his theory of relativity, we did not know whether the whole universe is just one conglomeration of stars or of galaxies. So galaxies, we now know, are basic building blocks of the universe. They are of different kinds. You can see various kinds of galaxies. There are about 1/4 of the galaxies look very nice and round. They're called elliptical galaxies. They're actually nice round ellipsoids. We now know they're very old galaxies. They're the first things that had formed, and now they've turned very old. Most of the galaxies, however, are nice and flat with spiral patterns. They're rotating very fast, and our galaxy is one of them. Galaxies don't like to live alone. They live in groups. They often interact with each other. We use anthropomorphic terms. We say they harass each other or strangle each other, depending on the nature of the interaction. And you can see how they interact with each other. Our galaxy looks like this. Our galaxy, we live around the sun, which is not quite at the center. Of course, this is not a real picture. You can't take a picture of the thing you live in. This is an artist's impression. It's very flat, and view from the top is this, right? So there are 5 spiral arms that kind of shows that the thing is rotating. If you stir your cup of coffee, you will see that a spiral pattern emerges. That's a natural thing, comes out of rotation. And if you look on the side, you will see that this is very flat. And the sun is not quite at the center. It's about 20,000 light years away from the center of the galaxy. And so what happens is that if you see, that is our vantage point of seeing the universe. So when you're seeing the stars in the sky, the stars that you see are all the stars around here in that small layer. And you see the stars in the sky. So the first picture I showed you are all stars that are in the layer in that limb of the disk of the galaxy. If you're looking towards the middle, however, if you're looking towards the middle, you see a whole band across the sky. And that's what we call the Milky Way. You can't see it from here very well. This is a picture from a place where I go quite often to do my observations. That's in the Andes, in Chile, in the Atacama Desert. The best place to do astronomy from, some of the best telescopes in the world. And this is the view. You can read by starlight. The entire galaxy is there, right? That's the center of the galaxy. You can't see it from the northern hemisphere. You really have to go to the southern hemisphere to see this view of. And then you also, if you've gone to the southern hemisphere, you know that you see two other galaxies with your naked eye, always there in the sky. They're called the Magellanic Clouds, and these are satellite galaxies of the Milky Way. The Milky Way has 40 or so satellites that we know of. They go around our galaxy all the time, right? So you can see what they look like. So this is, for example, actual picture of a galaxy that would look like the Milky Way. But of course we can't take a picture of our own galaxy. So that's a real picture. So then I'm going to turn it around and show you other, of course I can't turn a galaxy around, but I'll show you other galaxies which are kind of at an inclination, and you will see, if you see something that's side on, looks very much like the Milky Way. And now you can see, if you could observe that part of it, that's what our galaxy looks like. And this is a real picture taken by a fisheye lens that gives you the whole sky, and you can see what our galaxy looks like. And since we are not in the middle, we can, if you're looking towards the center, you can see that whole view of our galaxy. Our local neighborhood, we are, I told you galaxies don't like to live alone. We live in a pair. Most galaxies are in pairs. Our other half of the pair is called the Andromeda Galaxy. And these are now falling towards each other. And it's about a million parsecs, sort of 200 million light years away. And each of these galaxies have their own system of satellites, about 30-40 satellites that are going around them. There are many more. We've only discovered a few. Okay? And they're falling towards each other. They look very similar, and they're falling towards each other. Long ago in my PhD thesis, I actually did, one of the works I did was actually look at what's going to happen to the pair of the two galaxies, and found that they will actually they're coming towards each other, and they're going to merge to form a single galaxy in about 4.5 billion years. I said, our time scales are small, and not very small, and you can see this happening in other galaxies. So here's, for example, M81, M82, 3077, these three galaxies, and we can see that they're actually interacting with each other, and they're all going to merge and form a whole in a whole galaxy. And this is going to happen to us. So I'm going to show you a simulation that somebody did based on some of the early work that I had done on how the two galaxies will come and merge by a friend of mine in Toronto. And you can see it starts with a quote from my paper, but I wish I can start this, yes. So this is what's going to happen to the Milky Way and Andromeda. Think of these as the two galaxies. They'll come together. This is a simulation, mind you. And see how beautiful the merger of two galaxies looks like. And all this will take about 1 billion years or so, in 4.5 billion years. And they'll come together and they'll merge and form a single galaxy. And this is not fiction, because we see this happening all around us. I showed you some pictures before of galaxies merging as we see around us. So it's very interesting that galaxies are not islands, island universes, they also interact with each other, they exchange stars and exchange material. Right. So that's our current view of the universe, is that the universe itself is full of these galaxies. Where did it come from? So the idea is that it started from what we call was a big bang. This is a joke. It was no bang. It just started from a point in time. And now it's like 13.8 billion years old. And I'll show you how I know about it. It started from the general theory of relativity, which this man published in 1915, which describes the nature of space and time and how they're connected with each other. Very soon after the 1915 paper came out, it was in the middle of the First War. It didn't get much publicity till the war ended, but it was known in the Germanic, because it's written in German, published in Germany, and the German world is fighting the English-speaking world. So in the German-speaking world and associated academics, Einstein's theory was first dealt with in various ideas. And one of them was to apply the theory of space and time to try and figure out what the nature of the universe is, right? And one of the first people who did it was in the early 20s. After the war had ended, Einstein had moved to teach mathematics at the University of Sorbonne in Paris before he moved to the US. And one of his colleagues was this man called Joseph Lemaitre, who was a Jesuit priest who also was a mathematics professor at the Sorbonne. And he solved Einstein's equations, applying it to the whole universe. And he came to a very startling conclusion. The conclusion was that the universe could not be static. It was either expanding or contracting. It cannot be static. Einstein did not like it. And in a famous confrontation in the late 20s at a conference, after Lemaitre had given his paper, Einstein stood up and said, "Father Lemaitre, you are completely biased because you're a Christian priest. And you think that God created the universe and it had to start from a place where he himself believed that the universe had no beginning or no end." He asked the question, if the universe actually started, what was there before it? Right? So, but the mathematics is out there. It says that if GR is right, then the universe had to have a beginning and was either contracting or expanding. Einstein changed his field equations of general relativity so that this solution did not arise. And of course, a few years later, as you will see, he had to retract his modification. So now, looking at Lemaitre's solution, the idea was, Lemaitre said that the universe is expanding. As you will see, why it is expanding and not contracting. And if it is expanding, then if you take that movie and wind it back, it had to start from a place. And so he called it the cosmic egg, which kind of gave rise to the universe. Very unfortunate name, a long time ago. The other person who solved Einstein's equations was this man called Alexander Friedmann, who was in St. Petersburg at that time. Somebody who was also solving these equations. Very important a solution that he came to, very similar to Lemaitre's solution. He died at the age of 29. However, he published this in a Russian journal, which was later, this is later in the story you will encounter, his PhD student, George Gamow, took that knowledge with him to the West and came together with all the other people working in cosmology at that time to give a credence to what was happening. So the idea is that the universe is expanding. How is it expanding? Often this picture you see in textbooks. I really do not like this picture because it is like, it's telling you that the galaxies are spots on a balloon, and as the balloon expands, the balloon being the fabric of the balloon being the fabric of space-time, the galaxies are moving away from each other, right? Now that's a very, very odd thing to think about, because then you can ask the question, who's blowing into the balloon, right? I think a better way of looking at it is this. I mean, any of you baked bread or made cakes know that if you get together a ball of maida and put some raisins in it, and you know, some yeast, and put it in the oven, the thing becomes slowly expands, and then the raisins move away from each other, right? So that's kind of the model that we're thinking of. The universe is expanding, and the constituents of the universe are going away from each other, right? So that's called the Big Bang, even though there's no bang at the beginning. But the idea is that the universe started from a point in space and time, and it expands. And that comes directly as a solution of Einstein's equation. Yeah, and what I just said, so then winding backwards, the universe must have had a beginning. I'll come to Hubble's law in a minute. How do you establish this? You establish this by, as I said, all our knowledge of the universe comes from light. So you take the light coming from these galaxies, and you analyze them, and you turn them into spectra. If you analyze light through a prism or a grating, you get various kinds of spectra. You take a light that comes from one of these things, you get a whole continuum of colors going from red to blue. However, in that spectrum, you will get signatures of the various elements that are there in the system. So if the light comes through a cloud that is hot, it picks up certain wavelengths that are indicative of what's in that gas, and you see them as emission lines in the spectrum, or you lose certain parts of the spectrum and you call it absorption lines, right? So both the continuum and these lines give you a lot of information about what the light is traveling through. Here's a spectrum of the sun. It's been taken and folded to fit into this page, and you can see the wealth of information that there is. And a lot of our physics and chemistry that we do of the sky, of the heavens, comes from things like this, where each of these lines corresponds to a certain element, a certain chemical, in a certain state, physical state. And you have to understand that. Yeah. So a galaxy, its spectrum looks like this. And it has got hydrogen and oxygen and magnesium and sodium and things like that. And you see these emission lines and absorption lines, right? And you can identify them from the things in the lab that we teach our students. So people started doing, once it was established that we have these galaxies in the 1920s, people started doing spectral analysis of these nebulae that Herschel and Messier first talked about, right? These stars that don't twinkle. And then started realizing that these are very different from the stars that twinkle. And one of the things that they actually figured out was the fact that you could measure Doppler shifts. Doppler shifts are things where if the source of light moves, that makes those positions of those lines, the frequency and wavelength of these lines, change. Right? So if something moves away from you, the lines move more towards the red. And if something is coming towards you, the lines move towards the blue. This is a very common phenomenon. You see this in sound all the time. If something that is a source of sound is coming towards you, you see the pitch change because the wave is compressed as it comes to you. So here you are. So if you have a star and a nearby galaxy and a distant galaxy, etc., you can see that depending on how fast they are moving, those lines shift, and you can measure them. So here you are. I'm just taking you through a whole sequence. Here's a lamp in my lab, and you can see it's a hydrogen lamp, and you get a nice line there. Hydrogen is there in everything in the universe, stars, galaxies. If I measure the Orion Nebula, you see the same line there, and you can measure its position, and you see it's slightly shifted. If you look at a galaxy like that, you see that slightly shifted, but it's no longer at 656 nanometers, it's now 6-7 something nanometers. And you can go further and further, you see smaller and smaller galaxies, and you can see this moving further and further away. And this effect was discovered by Edwin Hubble. I'll come to that in the 1930s. But before that, I want to tell you another thing. So one of the things that you can measure for these things that are out in the sky is that you can measure their spectra and measure their velocity. So you know how fast they're moving. But you also need to find out how far away they are in order to make a kind of map of how things are moving in the universe. And that came from, again, I told you that's one of the major problems in astronomy. From the 1910s, a bunch of astronomers at Harvard, these were the Radcliffe College women astronomers. Radcliffe College was this women's college at Harvard at a time when, of course, women could not get degrees. Women could not, they could attend classes but could not sit for exams. The same in Oxford and Cambridge and Harvard. They started giving women degrees only in the 1920s. A bunch of women in Radcliffe College at Harvard worked at the Harvard Observatory, not registered for degrees, but they made these amazing discoveries. And one of their leaders was Henrietta Leavitt, who looked at repeated observations of the same stars in the sky and found that there were classes of stars that varied in brightness every few hours. And it went up and down, up and down, up and down, up and down, right? This one, for example, has a period of variation of 5 days. There are some that are hours, there are some that are longer. And what she also found was that there was a relation between how bright the stars were, or how massive they were, and their period of oscillation. So that led us to find out a whole new tool which is called standard candles. Standard candles are things which allow you to find the distance to something. If you, for example, had a 100-watt bulb or something like that, for which you knew how bright it was, and you took it at different distances from you, and you measured how much light is coming to you, you can say how far away something is. If you know how big something is, and you look at it from different distances, you can figure out how far away they are by measuring how big they are, or how they appear to you. So standard candles are things that if you know intrinsically how bright they are, you would be able to tell how far they are. And so by Henrietta Leavitt's discovery, she found a way of just measuring the period of oscillation of stars. She found a way of finding out how intrinsically bright that star is, which meant by observing it, you figured out how far away it is. So if you could observe these stars in other galaxies, you could find out how far away they are. So putting these two together, this is a nice picture of these bunch of women working at Radcliffe in the 1910s. And they did much more than what I just told you. Some of the fundamental discoveries of examining pictures of the sky and finding some of the principles of astronomy came from this group of astronomers. In the 1930s, late 1920s, Edwin Hubble came into this picture. And Hubble came into astronomy also in a very, very unusual manner. This whole story of astronomy has some really unusual characters. Hubble was a lawyer, trained in Chicago, who went to the First War to fight for the American army. And he lay in the trenches in France. And he promised himself, if he ever returned, if he lived at the end of the war, just looking at the sky from the trenches, he was in love with the sky and he would become an astronomer. He did survive the war. He came back to Chicago. He joined the school, the Department of Astronomy. And in his 30s, he became an astronomer. Right? And this first job was out in California, newly built Mount Wilson Observatory, the 100-inch telescope, the largest telescope in the world then. He was recruited to use this large telescope outside LA. And Humason was his assistant that actually took parts of the telescope up the mountain on a whole train of mules. And they were given this job of having this amazing telescope with a spectrograph for the first time and asked to do whatever you wanted. And Hubble turned his attention to this whole problem of Herschel and Messier, and to address the question, are these fuzzy things that you see in the sky, how far away are they, and how fast are they moving? So he turned his spectrograph to these fuzzy things. He actually went through Messier's list and Herschel's list and tried to get all of them, spectra of all of them. And he plotted this remarkable graph in 1929, which showed on the y-axis how fast these nebulae, these are nebulae from the Messier's list, how far they're moving, how fast they're moving, and on the x-axis, how far away they are. Now, I don't know about you. I mean, a lot of you come from various different subjects. If one of your students gave you a plot like this and drew a line through it like that, wouldn't you bin it immediately? However, it turns out it's a remarkably linear plot. If I show you, when I show you the latest version of this plot, it's actually a straight line. However, there's a huge scatter because of the huge uncertainties in measuring these things. Measuring both the velocity and also the distances. And what he was doing at this point was he was using Henrietta Leavitt's idea of finding Cepheids in some of these galaxies and measuring distances through them. He did that for some, but some of the others he did various other things. He looked at the size of the nebula and he tried to estimate the distance, etc. And that's the result. It's essentially a whole hodgepodge of things. But he came to this amazing conclusion that the further away a galaxy is, the faster it's going away from us. And that's a signature of the expansion of the whole system. His idea was the further something is, the faster it is moving. So why is everybody moving away from us? Have we done something wrong? Everybody's trying to run away from us? Or maybe we are a typical part of the universe and the whole universe is expanding, and this is why everything is moving away from everything else. So he jumped to this conclusion. He did not know that there was all this tradition of the solution of Einstein's equations that was being actually established as the fact that the universe cannot stay still and has to expand. Soon this result was noticed by Einstein, by Lemaitre. Lemaitre traveled to meet Hubble, and so did various other people who were working on Einstein's equations, and they realized that this is actually what was happening. So that's the idea. As the galaxies are moving away from each other, it just means that the thing itself is expanding. Einstein did not like it. Einstein actually thought the universe is infinite in time and space, and he, as you know, had changed his equation. But after Hubble showed that the universe is actually expanding, he went back. He said, it's the greatest mistake I've ever made, and he took back the extra term he had added to his equation to make the universe static. So by the early 30s, by mid-30s or so, it was established that the universe is expanding. And the idea is that the universe is expanding from a Big Bang. Now, it also means that because the universe is an isolated system and it's expanding, it's also cooling. Something that expands and it has its energy remains constant, it has to cool, which means that at the beginning the universe was very hot. And so it's called a hot Big Bang. And at the beginning of the universe, if the universe is very hot, and as it cools, as it expands, matter would form out of that energy that was there in the form of radiation. And the amount of matter that we experience would have come from that. But there would be a lot of that energy that would be left behind, but that would cool down. Okay. So this comes back another character I've mentioned before, and that is George Gamow, who, remember, was a PhD student of Alexander Friedman in St. Petersburg. After the revolution, Gamow, with his wife, escaped from Russia. Spectacular stories in his autobiography of how he did that. He came and worked with Niels Bohr in Denmark and with Eddington in Cambridge, and ended up in the US. He did an amazing thing. He said, look, as the universe expands and matter forms out of the radiation, the energy that would be left over would be still there, but it would be very cold. And you have to look for it. It will be the cosmic background radiation. And he estimated that the temperature of that radiation now would be about 5 degrees Kelvin, which is like minus 270 degrees, roughly. He estimated that, 1930s, in a paper written in Russian in a Bulgarian journal, which I have tracked down. It is just amazing, amazing paper. Prediction. Nobody believed that you could actually observe this. Till the 1960s. 1960s, Penzias and Wilson were two electrical engineers working for Bell Labs, trying to establish what you have in your pocket, mobile phones. They were trying to do wireless communication across the Atlantic. They were in New Jersey. There was a signal from the west coast of the UK, from Cornwall, and they were trying to reflect these waves from a balloon that had a mirror in the upper atmosphere, and trying to do wireless communication for phones. And they were using microwaves. Microwaves at 50 gigahertz. Your phone uses 5 gigahertz, right? And they found that wherever they turned their antenna, there was a background noise that they could not eliminate. So they wrote up a paper for Nature saying that there's a ubiquitous background noise that we cannot really eliminate. They first thought it was pigeon droppings. There were lots of pigeons living there. They cleaned the whole thing. Now, I also want you to know that this particular thing that you see in the background is called a horn antenna. It's got a very checkered history because they're using microwaves, right? Microwaves had not been used till the 1950s for anything. However, microwaves were first generated in India, in Kolkata. Microwaves come in this kind of range. That's the range in the electromagnetic spectrum of light here. And if you go to radio, the wavelength would be centimeters or millimeters, and the frequencies would be gigahertz. And after Maxwell showed that all kinds of radiation are the same, electromagnetic radiation, they only differ in wavelength, Heinrich Hertz produced radio waves which are of the wavelength and frequency that you now see in television or radio stations. Jagadish Bose in Presidency College set up his lab. He also came from the same Cambridge tradition of Maxwell, and went on to produce an amazing range of electromagnetic waves, which we now call microwaves. From the 1890s till the 1960s, you wouldn't see much application of microwaves. Now we use them everywhere. We use them in our phones, your routers, and whatever. But remember, this was Jagadish Bose. And I'll show you Jagadish Bose's original equipment that he set up in the 1890s in Presidency College. That's from his paper. He demonstrated this at the Royal Institution in 1895. You can see that he's producing microwaves and getting it reflected and detecting them. You see that antenna? That's his horn antenna. He calls it the collecting funnel. That's the same as this, right? It's got 2 Nobel Prizes. And it's a standard way of detecting. It's Jagadish Bose's design. Now, these guys found this background noise everywhere in the universe, but did not know how to interpret it. When they were writing their paper, somebody said, look, Princeton University is just 50 miles away. Go and talk to the physicists there. They've been looking for this. It's been predicted that there will be a background hiss in the universe. And so they went to talk to people in Princeton, and they talked to Debye and Peebles. Peebles got the Nobel Prize for this recently. And they realized that what they had detected was actually the universe itself. It's the remnant of the universe that is everywhere, because that's the energy that's left over from the original Big Bang. And that's the hiss. And if you take that energy and cool it down to what Gamow had predicted, 5 degrees, it turns out it's 3 degrees Kelvin, it will emit mostly in the microwave, exactly the kinds of frequencies that Jagadish Bose was measuring in the 1890s. And that's what this antenna was for. So they then found the fact that it's an amazing whole background radiation everywhere in the universe. You find this, it's there, and it's the remnant of the original Big Bang. That's a modern view of the microwave background with very small fluctuations. The fluctuations are of the order of 1 in 10 to the power minus 5. And the idea is that the universe started off at this energy, and those small fluctuations that were in there have now grown to become these large structures that you see around us, right? Now, so this is one of the things that prompted in the 1980s for Stephen Hawking's famous book, Brief History of Time, which a lot of you might have read. And when I first came to Cambridge as a student, Hawking was actually giving these lectures in my very first semester. I attended his lectures, which is giving public lectures, which led to this book. And one of the things that he was saying is, what do you think is going to happen to the universe? If really you've established now that the universe has started from a point, and by that time in the 1980s, one has established that there have been about 14 billion years that have passed, what is going to happen next? And it all depends on what the universe is made of. And I'll spend the rest of the time that I have, and I hope I have about another 10-15 minutes. I will talk about what that means in terms of what the universe is made of. So Hawking's idea in that book, which is now largely redundant, this book. It's what a wonderful book, but you will see why it has now become largely redundant. The book said, look, if the universe is made up of matter, and it has enough matter, then it can start off in an explosion and start expanding, but the combined gravity of that matter will bring it back. Just like you throw something up in the air, and of course the Earth's gravity pulls it back, right? But if, for example, you throw something up in the air with a velocity that can overcome the Earth's gravity, it will go on forever, like rockets do. So Einstein said, so Stephen Hawking's book proposes that, of course, he's coming from a tradition of research at that time, but in the popular domain, he was the first to put this idea that maybe the universe will come back if it has enough material. And so it will be called the big crunch. When the universe goes to a maximum, they'll come back. Or it will keep expanding forever. And so there'll be no end to the universe. And the only way you can discover what will happen is to figure out how much matter there is in the universe. Right? So that then became the focus of people trying to figure out how much matter there is. So you can either have a closed universe when it comes back, or it goes on expanding forever. And that will be the future of the universe. This is in the 1990s, when we now think that all these things are possible. So then the idea is, we'll have to figure out what the universe is made of. We know that what we are made of are things that are in the periodic table, right? Our bodies are made up of proteins that have carbon, phosphorus, hydrogen, nitrogen, oxygen, things like that. Is the universe made up of those things? And it turns out the answer is no. And this we learned in the 1980s and 90s. And this I'll show you, I'll illustrate to you how we came to learn this. There are many ways. The idea of matter and what matter actually is has been measured. One way is to measure it through the way light travels through the universe. Einstein's idea of the general theory of relativity was that gravity, as we see it, is actually a manifestation of the curvature of space and time. So what happens is, you have space, which itself is there, and you have light coming from one end of the universe to you, say, and if you have, light can come from one end of the universe through space to you, but if you have something massive, like a star or a galaxy, it locally distorts space. And if that happens, then if you have light coming from a star to you, it will bend, because it's going by space, and space itself is bent, right? So the prediction was that if you see a star, and if there is something in the way that is very massive, it will appear somewhere else. And if you can establish that, then you can measure how much matter there is here. And then ask the question, do I see it? Is that matter the same matter that I am made of? So this is this whole effect called gravitational lensing, which became a subject in the 1980s when this started being detected. You have a galaxy out there, here you are from the Milky Way and Earth, and you have lots of galaxies and clusters of galaxies in the middle, and the light is coming from far away through the universe to you. Can you establish whether it's come in a straight line or it's curved? You can do this if you know what things look like, in reality. So, for example, if you have a galaxy in here and you have something else which is a source of light, and you're detecting it here, and so light comes in different paths to you around that massive object, and if they're perfectly aligned, you will see that object not as a point of light, but you'll see it as a whole ring, because it's coming in different paths around it, right? And if that is slightly displaced, that ring will break up into multiple images. So you'll see the same thing in different places. This was predicted by Einstein. Nobody thought they would see it till the end of the 80s and 90s. You see these Einstein rings everywhere. We call them Einstein rings. They're everywhere. You see these rings. This is actually one galaxy, and you're seeing it as a ring because light is coming through different ways, and you can identify by making a spectral analysis all around the ring. It's the same thing. And then you can see different versions of the same thing. So here's a simulation of a friend of mine who made this to show that if you take a very complicated cluster of galaxies and you put in front of a simple picture, you will see different parts of it magnified in different ways, distorted, and in multiple copies. You can predict this by making these calculations, very simple geometric calculations. Do you see this? Do you see several copies of Sarah in here, in different ways? You do. Some of the spectacular pictures taken by the Hubble Space Telescope show that this is indeed what we see. If you look at galaxies, you will see that you're seeing these galaxy pictures. They're not like normal galaxies. but they appear to be distorted. And now we've started seeing the same galaxy in many different places. So actually, I can show you, it can be proved that this galaxy and that galaxy and that galaxy and that galaxy are the same thing. You can spectrally establish this. And by identifying them in different places, you can then measure how much matter there is in the foreground, in the cluster of galaxies through which that light is coming. These are spectacular PhD theses now, done by, a single picture like this can give you a PhD thesis. There's so much information in there. So much information in there. These are just some of the parts of single images taken by the Hubble Space Telescope and now with the JWST. Just look at the amount of distorted images you see in every image. And that means that when you see a galaxy, it's not actually there, it's somewhere else. The light is coming in a bent path to you. But what it has done, it has helped us understand the distribution of matter in the universe, even if you don't see it. And what it's telling us is that most of the matter in the universe is dark. You can only feel it by its gravitational effect. You don't see it in stars or galaxies. So that established the nature of dark matter. And this was the big thing in the 1980s and 1990s when I was doing my PhD. About 1995, the story further changed. And this is my last bit. Up till 1995, we knew that we see matter in the universe. Hawking has said, go look for matter and find out whether there's enough matter to turn the universe around. And the understanding was the stars, make about, the stars that you see in the sky, about 1% of the matter needed to turn the universe around. And the amount of matter that you were seeing in the universe was about 20% of that. So the answer was that the universe is not going to turn around. And the amount of matter that we see is mostly dark. Also, it came to this very uncomfortable conclusion that we actually know, because we know how much conventional matter, the matter that corresponds to the elements in the periodic table, is there in the universe, that much of this dark matter that we are seeing actually is not the same kind of matter. It has to be something different, something that is not represented in the periodic table by those elements. And so that opened up a whole bunch of different subjects in particle physics to try and figure out what other kinds of matter could there be. In 95, something else happened that gave this a further twist. And you remember the standard candle thing. Remember Henrietta Leavitt and her Cepheid variables. These Cepheid variables are very faint stars. You only see them in the nearby universe. You really can't find them in very far away galaxies to find out how far you can actually measure these distances. You needed to discover something that you can see in very far away galaxies. And that was discovered in 95. What was found, you really need a standard candle. What was found is that there are these supernovae. These are things that happen when a star explodes at the end of its life. There are certain classes of supernovae called supernova type 1a, which are standard candles. People discovered that they actually have a certain luminosity, certain brightness intrinsically that we can measure. As a result, if you can discover one of them, you know exactly how far away this is. And you can see that this is a whole galaxy, and you can see a star exploding. It can be as bright as the whole galaxy. So you can see them very far away. So the idea was that what you do is, I wanted to show you this. This is what these supernovae look like. They start at a certain time and they start getting brighter and brighter and brighter. They reach their peak in about 10 days, and about a month they decline, and then they are not seen anymore. So what you have to do is you have to catch them while they are getting brighter and brighter, and catch them, and if you can get the peak brightness of the supernova, that tells you exactly how far away it is. Okay? So this started off a whole bunch of activities to survey the sky and find out whether you can find these supernovae in other galaxies. And whole telescopes were dedicated to doing this. To take a picture of the same part of the sky every night, so you take pictures of 100 different parts of the sky each night, come back to it, do the same thing, come back the next time, come back the next night, and then digitally compare each night to figure out where things have gone up and become a supernova, right? And once you find something like this on a certain galaxy, you have to catch them here, remember? Then, so there were these telescopes in Chile, in Hawaii, in California, in the Canary Islands. Telescopes are dedicated to doing this. And then if you found such a star, then you ask the bigger telescopes to follow up. The telescope that I showed you in that famous picture, the 4-meter telescope that I worked with a lot in my life, is now completely doing this. For about the last 20 years, it was converted to doing just this and nothing else. It's called the Dark Energy Telescope. And so here I'm going to show you an example of how difficult this is to do it with the naked eye. Here's an example of one of these things. So here is a picture of a part of the sky taken one night, and there's another night 3 weeks later, right? And something has changed. If an astronomer looks at it and tries to figure out where things have changed, it's very difficult to do. I don't know whether anybody can see it. But what you do is you subtract this from this digitally, which you can do now. And you can see, now you can see it. There's a star that's exploded in that galaxy. Everything is, you can subtract out. So once you've found that, you ask the Hubble Space Telescope to take a much better picture, you can find that that's your supernova. And you can study it, you can measure. Once you know how, you can detect it till it becomes the brightest, and you know exactly how far away that galaxy is. Okay? So this started 20 years ago, and now we built up this entire library of galaxies in which supernovae have been measured, so we know how far away it is. Why is this so crucial? Okay. Remember Hubble's famous plot, and this is my last bit, so I don't know whether I'm running out of time. Remember Hubble's picture, which I said is a scatter plot that really didn't merit a line through it. What is this doing? This is putting velocities of galaxies versus the distance. And it's showing how fast the universe is expanding. Why is it doing that? The further away a galaxy is, the faster it's moving away from us. It's that slope of that line. The slope of that line gives you the rate of expansion of the universe. That slope. Now remember, in astronomy, one of the important things we have is that if you look at something very far away, you're actually looking in the past of the universe. Because light takes a long time to come to you. So we have a natural time machine in here. We are seeing something that is 1 billion light years away. It means that you are actually seeing the universe as it was 1 billion years ago. You have no idea what it looks like now. That galaxy might not exist. But you're seeing it at that time. So if you're going further and further away, you're looking in further and further in the past. Okay, so you really have to, if you want to know how the universe is evolving, whether the universe is expanding or contracting or anything, you have to actually look further and further away to see what it was like in the past. Now, this plot that Hubble made, if you look at it with 1990s technology, after the Hubble Space Telescope went up, in fact, the Hubble Space Telescope went up to discover Cepheid variables in other galaxies from space. That is why it was called the Hubble Space Telescope, to extend Hubble's work. And you can see now, the same plot that I showed you before, in 1995 looked like this. Now stay with this. That little yellow blob that I'm showing you was Hubble's volume. You can see with the Hubble Space Telescope, one had gone much, much further and established not only the fact that it's actually a very good straight line, not much scatter, but also you had reached distances out to which this expansion of the universe is pretty much uniform. Right? But you don't expect that to be, right? If the universe started off with an explosion and it's expanding and there is matter in the universe, you expect the universe to, that matter, that expansion to slow down slowly. So the further you look, you're looking in the past of the universe should have been expanding faster then, and now it should be slow. So you expect that particular line which gives you the slope, which is the expansion rate of the universe, to curve upwards. Because the more you look in the past, the slope should be higher. Hasn't happened yet. 95, when the supernovae were found, we could go into a regime where you could go so far away that you could find the curvature in the Hubble plot. Now remember, that yellow part that you see is what Hubble had done in 1929. In 95, that yellow bit, this is what happened after the first 100 supernovae were measured by these telescopes. Here, that little yellow square that you see in the corner is where the last plot was. And with the supernovae, one could actually go to gigaparsecs, much, much, much further away, and lo and behold, the surprise that came to us was that instead of this slope going upwards, it showed that as you go into the past, the universe was expanding slower then. And actually this shows that the universe is speeding up. Now that is totally contrary to expectation. What possibilities did Hawking give you in that book? That the universe can keep on expanding, slowly slowing down, or have so much matter that it will come back. Now we have another possibility, is that the universe is actually speeding up. Now gravity does not do that. You throw something up in the air, do you expect it to accelerate and go off? No. You expect it to, with the Earth's gravity, slow down and come back to you. This universe is not. So that tells you that the universe is not even made up of matter. It tells you that the universe is made up of something that pushes, not pulls. And this, astronomers in their wisdom called something called dark energy. I don't know why. This is given a lot of bad press to the name itself. So now you can see that in the entire, so energy and matter are the same thing, E equals mc squared. The universe is, this is what the universe is made up of. Hawking asked you, you have to know what the universe is made up of to know the future of the universe. We know that the universe is made up of about 30% matter, which is gravitating, which means that it pulls. 25% of that is dark matter, which doesn't correspond to any star or galaxies that you see. In fact, it doesn't correspond to any element in the periodic table. We are tiny. This is as far back from, Ptolemy, as far as Copernican that you can get. The fact that, there was a time when people thought that we were at the center of the universe and the universe has been made for us. We are not even made of things that the universe is made of. Right? This 5% of the entire matter energy of the universe is made up of the same things that we are made of. Our bodies are made of. These chairs are made of. 25% are particles that have nothing to do with the periodic table. And the rest of the 70% is not even matter. It is something that has no gravity. It pushes. And to this date, we don't know what that is. So this is what keeps us in business. This is what creates jobs in physics and astronomy. It tells you have to now figure out what this thing is. It's a completely new form, and it's the predominant constituent of the universe. It is what makes up the universe, and it's called dark energy. And this tells you that the future of the universe is not one that is going to expand forever and come back. In fact, it's going to expand forever. It'll just go on expanding, but will, and now it's accelerating, so it's not even slowing down. It was called something that dark energy. There was another name that was given to it. It was called quintessence, which is the kind of fifth element, as it were, which is also not a very good name because there are no four elements anymore. But the idea is that the universe is made up of something that is very, very alien to us. So I just would like to end with essentially saying that that's what people think will happen in the universe. We are here, but as it's a pretty grim future of the universe as the galaxies go far away from each other, and time and space will eventually probably be ripped apart. And there you are. The universe will not end with a bang, but with a whimper. I'll stop there. Thank you very much.